VITs, vacuum insulated tubing, it's a pretty simple concept. It's a double-walled pipe, so a pipe within a pipe. The overall concept of VITs are pretty simple. They minimize heat loss. They improve thermal insulation. We have, I think, over 10 end users, operators that are using VIT in the Gulf of Mexico, and a number in Canada as well. So overall, 40 operators. I think between 40 and 50 operators worldwide are using VIT.
Welcome to Geothermal Unleashed, where we're going to explore the cutting edge of geothermal energy. I'm Elizabeth Cambre from the Vallourec New Energies team, and I'm here to help educate and document geothermal's rise in the global energy transition. And I want to give a special thanks to Think Geo Energy. Joining me today is Corey Dufrene, the vacuum insulated tubular product lead at Vallourec. We're going to be diving into the role of vacuum insulated tubulars in the geothermal space. We're going to talk about what they are, what types of geothermal applications that they're used in, what are the challenges that they're addressing, and then all of the history, because there is some robust history behind this product. So, Corey, I want to thank you for joining me today. And
Thanks for having me.
you're welcome. I'd like to start by jumping into your background. Can you give us a little bit of history about your experience and how you got into the geothermal space?
Sure. So my background's in mechanical engineering. I've been in the industry for about 18 years, starting out in oil and gas, doing research and development for electric submersible pumps, and then moving over to premium connection development for the past decade or so. And then for maybe the past year and a half, I've been transitioning into this insulated tubing and geothermal markets. So it's been pretty interesting for me. There's a lot of diversity, a lot of innovation, and a lot of opportunity.
Well, that's great. Okay, so you are the product lead for vacuum insulated tubulars. So for those listening in, can you explain what we call them VITs, what they are?
Sure. So VITs, vacuum insulated tubing, it's a pretty simple concept. It's a double-walled pipe, so a pipe within a pipe, and within that spacing in between the pipes, there is an enclosed vacuum annulus. So very similar to what you would see with like an insulated cup, like a thermos, where you have an enclosed area where we evacuate the space. We weld the pipes together at the extremities of the pipe, pull a vacuum, and what that offers is very, very good thermal performance, thermal insulation, and it allows a lot of opportunities for uses that standard tubing would not offer.
Okay, so when and why were these types of pipe developed?
Sure, yeah. So surprisingly, VITs have been around for a while, dating back to the 60s. The development started in 1969 with GE in Alaska. And the initial development and implementation of insulated tubulars was for permafrost prevention. Basically, in Alaska, in some very cold regions, they needed a solution to keep the surface permafrost from melting as you got closer to the wellhead. If you're producing a hot fluid, in this case it was hot oil, the hot oil, the heat was transferring and heating up the ground. So yeah, back to the late 60s, GE developed this product for use in very cold Arctic regions where they needed to protect the environment at the surface. So what they were finding is that as their production fluids, the oils, gas, whatever, water was coming up to the surface, it was heating the area surrounding the wellhead and melting the permafrost, and that has a lot of environmental impacts and risks. So the solution was this insulated tubing, which kept the heat from escaping from the oil as it reached the surface and protected the permafrost and the environment.
That's fascinating. So, okay, so let's start with that application. What other applications have the vacuum insulated tubulars been used in, coming off of the permafrost application?
Sure. Yeah. So there are a lot of applications. The most popular, or I guess the biggest applications for Vallourec are in the Gulf of Mexico. So in Gulf of Mexico, the application, the most used application is what's called annular pressure buildup prevention. What happens is as in the spacing between tubing and casing in a well, you have a space in between, and usually that's filled with a gas or a fluid that is just stagnant. It's not moving. It's there. It's left over from the drilling or any workovers or anything like that. And when you have these hot fluids that are being produced, they could slowly increase the temperature of these annular fluids. And what happens is because it's a specific set volume, there's nothing there's nowhere for this fluid to expand to. So the pressure builds up. And as it builds up more and more, it can become a risk of collapsing the casing, or collapsing the tubing, and causing a lot of issues offshore. So that's one application. They're used as well in environments where a lot of the fluids that are being produced have a lot of condensates or paraffins,
Okay.
and these paraffins will condensate and solidify as the temperatures drop. So they are in liquid form at downhole, but as they get closer to the surface, they cool off, and it's almost a wax sort of buildup that you would see, almost kind of like an artery being choked off. So the VITs, these insulated tubings, are installed to keep the temperature within your fluids high and not bleeding off or not losing a lot of heat as they're being brought up to the surface to keep these paraffins and these solids from solidifying.
It's smart. That's smart.
Yeah. Yeah. Additionally, we have a lot of applications in Canada in the steam injection market. So in that particular case, for a lot of it's steam assisted gravity drain or heavy oil production. So the way that these applications are done, they require two wells. So you have an injection well and a production well, and with the injection well, steam is injected into the top, the upper well, to increase the viscosity or decrease the viscosity of the oil, so it will flow more easily through the production well at the surface. VITs come into play because they really improve the efficiency of the steam injection. You don't lose as much heat going down from the surface to the production zone, so you can spend a lot less time, or an operator spends a lot less time, a lot less money injecting steam for the, you have a much more efficient operation. So they've become pretty popular in the steam assisted or steam injection side of things as well.
That's interesting. So for a SAGD application, the VIT would go in the well.
Yes.
Okay.
Yes.
So what would you say? How many wells out there have vacuum insulated tubulars, at least from Vallourec's standpoint?
Yeah, that's a good question. I know on the Gulf of Mexico side, it's in the order of about 750,000 feet of VIT that are currently installed. The number for Canada for steam injection is a little hard to track because the wells that are installed are more or less temporary. They will install, run the tubulars in the injection well for 1 month, 2 months, 3 months, pull them, and then move to another application. So there are hundreds of thousands of feet of VIT that are in process, that are in production, but they cycle through. So the number of feet that are currently downhole in Canada is a hard number to track, but Gulf of Mexico, those are more permanent installations. So yeah, over 750,000 feet of VIT in the past 25 years, so since 1999. And that's a pretty steady, established market. We have, I think, over 10 end users, operators that are using VIT in the Gulf of Mexico, and a number in Canada as well. So overall, 40 operators, I think between 40 and 50 operators worldwide are using VIT.
Can you talk a little bit about where it's manufactured?
Sure. So the global manufacturing facility for VIT is in South Louisiana, in Houma, Louisiana. We have a single line that produces the VIT. So they receive the pipe from our various steel mills, and they perform all the operations, the welding of the pipes. So the ends of the pipes are welded together. They perform all the operations for creating the vacuum, securing the vacuum, all of the manufacturing processes for the VIT are performed at our shop in Louisiana. Threading services as well. So when it leaves the facility, it's ready to be installed. There's no special equipment for installation, none of that. So it's a self-contained component of a system.
Okay, it's very cool that it's manufactured in Houma. So I assume that this facility has been manufacturing the VIT for a couple decades.
Yeah, so the shop first came online in the mid 90s, and has been servicing Gulf of Mexico primarily. That was the initial reason for the location, just because of its proximity to the Gulf, and all the operations there. From that, the market for steam injection started in the late 2000s, early 2010s, and the need was identified for insulated tubing. So, with that, the shop, the VIT shop in Louisiana, was able to add on that capacity as well. So right now, for all of Vallourec, all the VIT manufacturing happens at our Houma facility.
That's great. Okay, so now let's talk about geothermal. Why are vacuum insulated tubulars needed in geothermal?
Sure. Well, I mean, it's the overall concept of VITs are pretty simple. They minimize heat loss. They improve thermal insulation. So any opportunity to maintain more heat within your geothermal fluid is more opportunity for thermal power. Whether that is for electrical power production, whether it's for direct use in geothermal, it increases your efficiency from downhole to surface of your temperature. So you're able to produce more heat, more power than you would otherwise.
Okay, so let's talk about the power generation, and you've got a well. So what are the key components then that you need in order to maximize the power output of a given well? So heat, you said, is one.
Yeah, I mean it's heat, it's flow. So the more volume that you could flow through, the more water that you're pumping up to the surface, the more that you are producing, not only from a temperature but from a volume standpoint, that the more capacity that you have to generate power. Um, so going even beyond that, um, the type of fluid that you use is also important. Some systems that are, we haven't really touched on differences between what we call open systems and closed systems, but closed systems give you the opportunity to kind of control and maximize or optimize the fluids that you use as well. Some, a lot of systems are just using water, which is a good thermal conductor, but there are also opportunities of using supercritical CO2, using ammonia that have higher heat capacities, so you're able to extract more heat from the environment, from the reservoir, and then the VIT helps to maintain that going up to the surface. So your overall efficiency goes up of the system. You have it, the easiest way to think of it is you have a capacity for heat based on your well, based on your reservoir, based on your downhole temperatures. You have a certain potential to extract, and by optimizing the system, whether it be your working fluid, whether it be by using VIT or your surface equipment itself, you're able to try to improve and increase that efficiency as much as we can.
Okay, so let's say, I've got a couple questions I'm going to ask based off of what you've just said, but I want to start with, let's say that you just use a regular pipe and you're trying to get heat from the reservoir to the surface. How much thermal loss could you have by just using a regular pipe?
A lot. I mean, that's a short answer. Obviously, there are a lot of variables that are in play. It depends on the temperature of your reservoir, of the formation as you get closer to the surface. Some wells are very hot, until you get very, very close to the surface, then taper off very quickly. Some have more of a linear drop off. So that affects it as well. Your flow rates, your velocities of the fluid as you go, even the characteristics of the flow itself. If you have more turbulent flow versus a more laminar type, which depends on the friction of the friction factors, your pipe, the roughness of the pipe, or whatever material that you're using, really affects the flow, which affects the heat that's transferring out of your fluid. But, and again, there are ways to mitigate losses, but there can be substantial losses by using standard pipe, and that's an opportunity that's where the VIT comes in. It's depending on the situation. There are some types of geothermal wells or geothermal applications where using a standard pipe just isn't realistic. The amount of heat loss that would be, closer to 75, 80, 90%, which makes it, from an economic standpoint, it's not viable. So the use or the adaptation of VIT allows these wells that would normally be unproductive or unviable to be able to use for power generation or for direct heat and direct use in geothermal.
Okay, so I want to talk and distinguish a little bit about like conventional geothermal and next generation geothermal, and how the VIT has application in the next generation geothermal, like the closed loop or advanced geothermal systems, and then the engineered geothermal systems, or EGS. But before I do that, I just have a question. Do you think then that the deeper you go, so now with next generation geothermal, we're going deeper and deeper, is there more potential for thermal losses because we're now drilling deeper wells to execute geothermal?
Sure, absolutely. I think the easiest way to think of it is from a temperature differential standpoint. If you look at downhole, whatever your temperature is, say you're at 200 C, 300 C, and then comparing those temperatures to your reservoir as you get your formation, as you get closer to the surface, as you're approaching your wellhead, that temperature is going to drop lower and lower. And as that temperature drops of your formation, the gradient, that delta between the downhole temperature and your formation goes up, and that's where you lose heat in a standard system. Anytime you have that difference in temperature, the overall system wants to balance out, wants to normalize, and so the hotter fluid wants to cool off, and the cooler fluid wants to heat up. So you're constantly fighting that heat transfer between the two fluids. And as you increase that that discrepancy between your formation temperature and your fluid temperature, that potential of heat transfer and heat loss goes up.
Got it. Okay, so let's talk now about maybe you can just describe, because I always think there's so much terminology in geothermal and it's so easy to get confused. So if you could just describe what closed loop or advanced geothermal system is and how the VIT is applicable in that, and then also explain what enhanced geothermal systems are, or they sometimes say engineered geothermal systems or EGS.
Sure. Yeah.
So explain that, and then how VITs are applicable for that application.
Sure. So your first point, the AGS, the advanced geothermal systems. When we talk about closed loop, that means that there is no access or no interaction with whatever your geothermal fluid, whatever your working fluid is, with the environment. So it's completely closed off. The interaction is just from a heat transfer perspective, the convection, the conduction between your formation and your fluid. Similar to what you would see on the surface with like a binary power generator, an ORC, where you're transferring heat from one fluid to another, but there isn't any direct contact. And that's the main thought or theory with the closed loop system. There are advantages to AGS systems, and mainly from environmental impacts. Is there you don't have any fluid losses into your formation into the reservoirs. You can control the environment a lot more. There's less exposure to any sort of toxic or any sort of environmentally or gases that could negatively impact the environment. And you have again, it's a lot more controlled. It's closed. It's a type of system where, depending on your environment, it is very advantageous. Where if you're in a very remote location and you don't have easy access for supplemental water, if you need to constantly replenish the system, if you're losing, if you're in an EGS, which I'll get to in just a second, or a type of system where you have a very porous rock where you're losing your fluid, if you're pumping fluid, yeah. But and then moving on to EGS, so the enhanced or the engineered systems, those take that initial step from the conventional in the fact that they use engineering methods or enhanced methods to increase the heat transfer, or the amount of heat that you're able to absorb from the earth, from your reservoir, from your formation. The main differences between the EGS and the AGS is that closed loop that I'd mentioned before. A lot of the EGS systems are dependent on some interaction with the formation. Depending on the type of company or the type of application, some companies, their EGS systems use a fracking network. So the network of fracking, what that does, it's really advantageous, because what you do is by adding these fracking, it's almost like a capillary network, which really increases your surface area that your fluid is exposed to. So as you increase the surface area, the amount of heat that's going to be transferred from the well to your fluid greatly increases. It comes with some technical challenges and then some risks. That there's not as it's not completely closed off to an environment. So there's the potential for some fluid losses, and similar risks to what you would see in shale gas or the initial, fracking, where you would there are geological concerns that need to be verified, and then your communication between your wells and that sort of stuff. But the potential is very high, and the amount of heat that you're able to extract makes it makes it very, I guess, advantageous. It's something that operators and companies are really looking into because the potential is there.
So look, going back to closed loop, so one thing that is good is you could use a single well bore. And can you talk a little bit about how the vacuum insulated tubular kind of helps with a single well bore, where you
Sure.
don't have to have an injector where you're injecting cold fluid and then heating it up in the reservoir and then producing it out of another well?
Yeah. So the single well, the closed loop with a single well bore, that system is entirely dependent on VITs, on insulated tubing. Um, the concept behind a single bore closed loop system is you have a casing that would be drilled down to whatever depth you would be, and then inside that casing is a tubing string, and also the casing is capped at the bottom to enclose the system, so you don't have any communication. And fluid is pumped from the surface, typically in the annulus between the casing and the tubing, is pumped down from the surface. As it's pumped down, it's being heated up by the formation. Um, and then at the bottom, it returns through the inside of the tubing. So it's a continuous sort of cycle. It's being heated up on the way down in the annular space between the casing and the tubing. And then on the way up, it's carried up to the surface. The problem is that if you use a standard non-insulated pipe, uh, as you're coming up to the surface, that hot fluid, it sees that temperature differential between the fluid in the annulus between the casing, and then your production fluid as it's coming up to the surface. So you have a lot of heat transfer, and you lose all of the heat that you're gaining on the way down. So the overall efficiency of the system is very low.
Okay.
By using an insulated tubing, so that what the VIT does is it allows the heat. You're pumping the fluid from the surface. It's outside of this vacuum insulation, so it's absorbing the heat of the formation, and then on the return trip, as it's coming from downhole up to surface, it's insulated and protected by this vacuum. So the heat is maintained going up to the surface, and you're able to harvest and take advantage of the heat that you gain on the trip from the the surface downhole.
Okay, so now let's just do a quick comparison to what the VIT, like if you were to use a VIT in the EGS, where you've got the two wells,
Mhm.
where would you put that and what would be the purpose?
Yeah, so in an EGS system, VIT has a use as well. It's basically any opportunity where you want to try to preserve heat and minimize heat losses. So on the injection side, there's not really much of an advantage to use VIT. At that point in the system, you're trying to absorb and gain as much heat as you can from the well, from the formation. And the same thing, if you're in a lateral, if your injection well goes into a lateral and you have your fracking and all that, you're still in the phase where you're trying to extract as much heat as you can. The production side is really where insulated tubing has potential. But again, that potential is maximized as the delta, as the difference between your fluid temperature and your formation temperature increases. So if you're really close to your maximum depth, the temperature differential between your fluid and the formation is not going to be very high. So the efficiency or your losses using a standard tubing are not going to be very high. But as you get closer to the surface, as the formation cools down, the formation is trying to cool down the production fluid as well. So that's where the VIT comes in and is able to insulate the fluid as it gets up to the surface. So there are potential with AGS and EGS systems for VIT.
Okay, so you had mentioned earlier that we talked about how there's multiple factors that go into getting that maximum power output. So you had said, that temperature, getting the temperature from the reservoir to the surface, and then you also mentioned flow. So what are the types of sizes of VITs that you could use that could help increase the flow rate? Because the larger the diameter of your pipe, the more flow you could get.
Sure, yeah, and typically when we talk about tubing sizes, we're talking about 3.5 inches, 4.5 inches, 5.5 inches, and those are the historical, I guess, historically have been the popular sizes of VIT. Most of the sizes that are downhole and have been manufactured in VIT are between that 3.5 inch and 7-inch range, where you would have, for example, a 7-inch VIT would have a 7-inch outer tubing and then a 5.5-inch inner tubing. So, your inner diameter would be about 5 inches. And then going down to 3.5-inch outer tubing to like a 2 3/8 inch inner tubing. But with that being said, we do have historical data where we have produced VITs going up to what would be, I guess, the typical casing sizes. So the largest to date that has been manufactured has been a 16-inch outer pipe by 14-inch inner pipe. So there's a lot of potential as you get, as in geothermal as well, as the technology starts to improve and adapt, as the wells get deeper, as the temperatures get higher, the need and potential for larger casing or insulated casing, tubingless applications, are really kind of coming to the surface or coming to the forefront, and it's an opportunity that VIT can handle. It's the current technology allows for us to go to the sizes that are needed if we're talking about large volumes of produced fluid. If you want to, if your thermal power if you're trying to get into the 10, the 20 megawatts of thermal power, you need to produce a lot of volume. And with the smaller tubing, if we're trying to use a standard tubing size, 5.5 inch, 4.5 inch, it's quite difficult to produce that volume of fluid, with the pressure drops, the parasitic loads that you would have from friction losses. It's really advantageous or necessary to increase your tubing size. And even in the vacuum insulated space, it is something that Vallourec has a history of and has the capacity to do.
Wonderful. So are there any notable success stories or case studies, or how many of these in the geothermal space have actually been ran? Can you just talk a little bit about what the track record has been?
Sure. Yeah. And I had mentioned previously the track record and history that we have of the VIT itself in the oil and gas sector. With between 40 and 50 operators, about 1.25 million feet in the past 25 years that have been used. But as far as the geothermal sector, we've had a handful of applications where we've tested closed loop systems, where we have investigated potential for EGS systems as well. And this transition has been starting with Vallourec since 2020, when we had our first geothermal test well. And since then, we have slowly ramped up, slowly built our reputation, slowly promoted the product and the applications and potential of VIT in the geothermal sector. So it has ramped up. We have in 2025 we have a number of applications and installations that are planned with VIT. in the geothermal sector. It's something that continues to build up, and as we as the technology and as the heat requirements, the temperature requirements go up, the demand and use of VIT should increase as well. The potential of using VIT becomes a lot more viable and a lot more necessary.
Okay, so I imagine that there could be challenges that you could face with increased temperatures. So what are the biggest challenges you face when you're promoting this technology or doing the design work?
Sure. Yeah. It's an interesting exercise for me. As I mentioned, this VIT, the technology has been around for about 50 years, 50 plus years. The technology was developed for lower temperatures. This over the past 50 years, the processes and the product has evolved, but to the needs of that environment, and that environment were lower temperatures, so lower than 200 degrees Celsius or about 400 F. The environment was more corrosive, where we needed to adapt the product by using stainless steel, high chromium steel, making improvements to increase the longevity of the vacuum in a corrosive environment where we have to worry about hydrogen permeation or calcium chromide, and that has been those have been the main challenges of VIT in the oil and gas sector. The challenges for geothermal are very different, and you had mentioned temperature. The temperature that we're getting to, these extreme temperatures where we're talking upwards of 350 to 400 degrees Celsius, those present an entirely different scope of challenges to the product. So first and foremost, it's the material itself. The steel, as you get to 400 Celsius, you're approaching some of your tempering temperatures of the steel itself. So you have like the temperature durations become nonlinear. It's harder to predict how the temperature or how the material will behave at those high temperatures. The other issue when it comes to VIT is that you have a pipe and pipe, and these pipes are welded together. So the weld is under an enormous amount of stress, specifically as you get closer to the surface. And I think this is probably the 10th time I've mentioned temperature differential, but when you have a very hot fluid that is heating up your inner pipe and an ambient or very low temperature from the formation, the thermal expansions are working against that weld. They're wanting to pull it apart. So we have some techniques, some process techniques to alleviate those situations, to kind of compensate for those temperature differentials. But as we go higher up, as we push the limits even further, all of those concerns need to be expanded. All of those risks need to be mitigated, and there are a lot of challenges. And then with geothermal, one of the main concerns beyond just the temperature is the longevity of the product. The VIT is a product that is an investment. It's not it's a costly product. Just from the amount of material that are involved in its manufacturing. So some of the needs for geothermal, the product needs to last for a long time. That isn't necessarily the case when it comes to oil and gas applications, especially steam injection for VIT. It's easy enough to pull an injection string after an operation, an injection operation, to swap out a VIT if it's been damaged over time or anything like that. VITs and geothermal are really require long use, long durations without any drop in performance, without any need for maintenance. And the product is designed for it, but the validation or the testing, the quantification of that is something that needs to be done and needs to be promoted. And operators, companies, geothermal operators need to have confidence in the product and confidence that this product that was developed for oil and gas applications and lower temperatures and more corrosive environments is robust enough to handle a different set of challenges that we see in geothermal.
That's really exciting. Well, Corey, I think we're out of time, and I want to thank you for joining us today and walking everyone through vacuum insulated tubulars and the role that they're playing in geothermal. And I want to thank the listeners for joining us as well on this episode of Geothermal Unleashed. And I really hope that today's discussion has sparked new insights and deepened everyone's understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working together to unleash the full potential of geothermal. Thank you.
Thank you.